Welcome to lesson 6.8, Stoichiometry, Moles to Grams, part 1. So make sure you title your notes this, and these are the two things you need to recall from the previous lesson. So far in this unit, we're talking about how to make medications, and we're mainly talking about, at the final stages, when I want to make a 500 milligram pill of this, or aspirin, how do I do that? So just a couple of general reminders before we start. When we're talking about an element, we have a single atom by itself. All right, so here, let's say this is C or carbon, one element by itself. On the other hand, when we're talking about a molecule, we're talking about at least two elements bonded together or combined together. So let's say the yellow sphere is N and the three blue spheres are H3. So if I have one N stuck with three H's, we call that a molecule. And this molecule is called NH3. So whenever we're trying to create a chemical reaction, we often combine elements and molecules together or molecules and molecules together so that their atoms can rearrange and form new types of molecules. So when this occurs, we often have a recipe written in the form of a chemical equation where we write the amounts we need, like we do here in red in front, and we call that the coefficients. So this part is another part of review, and I also want to remind you that when we write the coefficients in red up in front, that this doesn't mean we have just two mg's and just one molecule of O2 to make two molecules of MgO. And that's because if we just did this by two atoms of Mg, one molecule of O2 to make two molecules of MgO, that is way, way, way too tiny for us to deal with, right? So this doesn't represent two Mgs. It represents the fact that we have 2 moles of Mg. And remember, each mole is 602 sectillion things. So this means I have 2 times 602 sectillion mgs. And I'm going to combine that with 1 mole or 602 sectillion O2s in order to make 2 moles or 2 times 602 sectillion MgOs. Right? We have to multiply by a mole or this huge number so that we can be able to even see the reaction occur. Right? So you might be wondering, or probably not wondering, why this number 602 sectillion? Why can't it just be 1 sectillion or a number that's easy to do math with? And that's because when we're working with these reactions, right, we're not going to sit there and count out 2 times 600 sectillion atoms or pieces of Mg. It just doesn't make sense. No one has time to count out this much stuff because it takes way too long. So we're going to take a lesson from bakers and baking, and we're going to weigh this stuff out. So instead of counting out these numbers, we're going to weigh this stuff out. And in order to weigh this stuff out, we need to understand why we get this number 602 specifically and not any other number. Okay, so it turns out this Italian dude, Avogadro, did a little experiments because he was the one who discovered how much to put in a mole, right? So he was the one who said 1 mole is going to be 602 sectillion. So here's why. So what he essentially did was he took an element like sodium and he weighed out 22.9 grams of sodium. And he found out that when he weighs this amount of sodium, he discovered there were exactly 602 sectillion elements, just about, or 1 mole, right? Normally, this number is our average atomic mass, or the mass of one atom, right? Averaged together based off of all of the isotopes, meaning I have the same element with slightly different number of neutrons. So he weighs out about this much, and it turns out there are 602 sectillion, or 1 mole, sodium atoms. And then he took carbon. So when he weighed out 12.01 grams of carbon, turns out that there was also 602 sectillion atoms of carbon, or 1 mole. So he did this again and weighed out 16 grams of oxygen and 1.01 grams of hydrogen. And it turns out in all of these cases, when he weighs out this amount from the periodic table, it turns out there is exactly 602 sectillion elements of these, or exactly 1 mole. So for all of the elements in the periodic table, this number down here has a double meaning, right? So all the average atomic masses could be the number or mass of a single element, but it also counts as the mass of exactly 1 mole of that element. So the molar mass is the same as the average atomic mass number, right? It's the same as the average atomic mass number. And that mass number just means I have 1 mole of that element, right? So if I weigh out this many grams of sodium, I will have 1 mole. If I weigh out this many grams of hydrogen, oxygen, or carbon, I will have 1 mole. If I weigh out 52 grams of chromium, I will have 1 mole of chromium. 54.94 grams of manganese, Mn, I will have 1 mole, right? If I weigh out 69.72 grams of gallium, I will have exactly 1 mole of gallium. So it makes our chemistry a lot easier because it just happens to be the same number on the periodic. Okay, so now that we have the definition down from the last slide, right, how is this useful? Well, if I have a chemical equation, this chemical equation doesn't really make sense, but let's just use it anyway, where I have 1 mole of Na, and I know I need 1 mole of N. I don't need to count out how many atoms I need anymore. I can just weigh them out. So when I'm doing an experiment, I'm not going to sit there and count out 602 sectillion NAs. I can just figure out the weights. So if I have 1 mole of Na, how many grams do I have or need to weigh out? Well, all I need to do is look at Na. It's here, it's also here. Na's mass is 22.99 grams, so I'm going to have 22.99 grams of Na, right? Because 1 mole of Na is always equal to this number, the molar mass, or the average atomic mass. On the periodic table. You can probably also figure this one out on your own. If I have 1 mole of N, or nitrogen, how many grams will I have? Well, all I need to do is look at my periodic table. N is here. Average atomic mass of N is 14.01, so I will have 14.01 grams of nitrogen. Super simple, minimal math, definitely a thing that scientists love. Okay, so what if I double this? If I have 2 moles of Na, how many grams do I have? Well, if one of these, 1 mole of Na is just 22.99, I just need to multiply it by 2. So I have 2 moles of Na. That would be 2 times this number, 22.99. So if I multiply 2 times 22.99, I will get 45.98. So what if I have the same thing going on with N? So if I have 2 moles of N instead of 1 mole of N, how many grams do I have? Well, if I have 2 of these amounts, I'm just going to do the same thing. So 2 times 14.01 grams. And that will get me 28.02 grams, right? Okay, so what if I have molecules in this case, right? So let's say I have molecules like H2O and NH3. What do you think we need to do here? See if you can guess that. So hopefully you suggested that we're just taking the periodic table's average atomic mass for two H's because it says H2 and then 1O and then adding them all up together, right? So whatever the average atomic mass is for these two plus oxygen, we're just going to add them together, right? So if I look up hydrogen, hydrogen's mass is 1.01. So it's just going to be 1.01 times my subscript 2, right? You can also add them up together if that works for you. I just like to multiply, right? Same, plus O. What is O? O is 16. So 16, I don't need to multiply this one because I only have one O because my subscript is 1. So my answer is going to be 1.01 times 2 plus 16, which will give me a total of 18.02. Right, so I would have 18.02 grams. I'm going to skip question number 2 and 4 and have you try those on your own. So what if you have 2 moles of H2O? So here, this is how much I would have if I have 1 mole of H2O. If I have 2 moles of H2O, how many grams would I have? Well, I would just take this whole number, 18.02 grams of H2O, and then I would multiply it by the 2 moles that I have. So if I multiply that by 2, I'm going to get 36.04 grams. So go ahead and try questions 2 and 4 on your own. I'm going to go, oops, this should say NH3. So once you try these two on your own, when you unpause, I'm going to have the answer with the steps shown. So for question number 2, if you have 1 mole of NH3, if I look up on the periodic table, N has an average atomic mass of 14.01. Right. There are 3 H's, so 3 times the average atomic mass of H, or 3 times 1.01. So 14.01 plus 3 times 1.01 will give me 17.04 grams. Right. In question number 4, if you have 2 moles of NH3, right? So if I have 2 moles of this instead of just 1 mole of this, how many grams will I have? Well, it's just 2 times however much a molar mass or 1 mole of NH3 weighs, right? So 2 times 17.04 grams, which will give you 34.08 grams. Okay, on to the hardest type of problems. So if you have 1 mole of this complicated molecule, LiNO3 2, can you figure out how many grams you would have? Right. So you might recognize the pattern that for every element that we have, we need to figure out their average atomic mass on the periodic table and add up however many we have. Right. So notice here that I have 1 Li. So let's look that up on the periodic table. Li has a mass of 6.94. Right, so this is going to be 6.94 plus how many n's do we have? Well, here's the tricky thing. All right, so n is going to go in here. Notice the subscript for n, there's no number. So technically, I only have one n. But remember the 2 outside of the parentheses means I have 2 of these NO3 things. Right, so another way to show this or to write this out is this 2 means that I have NO3 and then NO3 again, right? So I actually have 2 N's. Another way I can think about this is essentially that this is like the distributive property in math. So if I take the 2 from outside, I just need to multiply it by 1 for the subscript of n. And we actually have 2 times whatever the mass of n is, 14.01. Right, and we're going to add that with however many O's we have. Right, so notice the 2 on the outside. I'm going to multiply it by how many O's I have. So within the parentheses, I have 3 O's. But again, the 2 means I have 2 sets of these O3s. So 2 times 3 is going to be 6, right? So technically, I have 6 O's, and that's going to be 6 times whatever the weight of O is, or the average atomic mass of O, 16. So 6 times 16. Probably should have made all these the same color. O3. There we go. And if I look at this side, right, if I count 3 plus 3, that's how I get 6 O's. So anytime I see a number outside of the parentheses, I'm going to multiply into the parentheses, just like with the distributive property. But since Li is outside of the parentheses, I don't need to worry about that. So this is one key thing that sometimes can be tricky for others, right? So know that you just take the 2 or the subscript on the outside, this thing, and we're always going to multiply in with parentheses. So that's how we figure out how many n's and o's and how many elements we have on the inside of the parentheses. So once I have this set up, I just need to type it into a calculator and I will have my answer. Okay, so notice when I'm typing things into my calculator, I'm also including the parentheses because remember PEMDAS, we need to multiply first before adding, so on and so forth. So just in case, make sure to also tell your calculator to do that as well. So when you multiply everything in, you would get 130.96 grams. So our answer, if you have 1 mole of LiNO32, you would have 130.96 grams. And again, if you have 2 moles of this, once you figure out how much you have in 1 mole, You just need to double it. So 2 times 130.96 grams that we got from here. And that will give us a total of 268.86 grams if we have 2 moles of LiNO3, 2. Right. If you do have any clarifying questions, feel free to ask me in Zoom class or Zoom class tomorrow. So at this point, you should be able to complete the quiz questions on the next slide.